All right, today I want to talk about the standard normal distribution. Actually, I just want to talk about the normal distribution. If you look at the figure, you can see that this normal distribution looks like a bell. In fact, it's called often the bell curve, and there was even a very controversial book called The Bell Curve, and I'm not going to get into that at this moment. I actually addressed that in a research methods textbook I'm talking about, because that was a terribly stupid book that was written, very discriminatory. There are distributions that apply to continuous variables, and I know in the past week, a couple weeks ago, we talked about one of the distributions already that was continuous. And now let's move into the normal distribution. And this is escaping my mind what that name of that distribution was. That's why I'm hesitating here. But when we're dealing with continuous distributions, we have what are known as probability density functions. So there's always probability distribution functions. Those are the functions that are used to draw these wonderful graphs, right? These wonderful figures where we're trying to predict some y value, the y value being on this y-axis, vertical axis, and the horizontal axis being the x value generally when you write an equation. So there's probability distribution functions, and when we have, I remember, it's uniform distribution. That's the one we dealt with before, yeah. So when we're drawing a distribution for a continuous variable, we call it a probability density function for a categorical, or I should just say discrete variable, because discrete includes categorical, ordinal, counts. We have a probability mass function. So this is a probability density function. As I mentioned, it's bell-shaped. The equation, or the PDF as we call it, the probability density function for this beautiful curve is here. It's written here, and it's actually showing you a standardized version of this. We'll get to this z value shortly. Beautiful distribution, right? Just like any PDF or any probability distribution function, whether a PDF or a probability mass function, it must summate to 1, or in this, I don't write the equation here with the integral. It must integrate to 1 because this is a continuous variable. Going over calculus is beyond the scope of this course. However, if you're interested in it, I do have a video in YouTube that shows you the proof of this distribution, that it's a PDF, and also that its mean is mu. Well, what its mean is, and actually we've already calculated the mean and the standard deviation, but show you exactly what the mean is and what the standard deviation are. So mu stands for mean, for population mean. Again, it's a Greek letter versus a Latin letter for sample, and sigma is a standard deviation, which is the square root of the variance. And I mentioned mu is location and sigma is spread. I think the other week I talked about moment generating functions, and again, that's beyond the scope of this course. I'm just letting you know what they are. And in my videos, I think I show both how to find the mean and the standard deviation using multiplying the value by its PDF, or by using moment generating functions. Moment generating functions become very useful as we get more complicated distributions. So they're actually really easy to deal with, but you have to understand what they are. And again, that's beyond the scope of this course, but if you're interested in it, I have videos on those too for the normal distribution. I'm working on there's other distributions I want to work on next. If we look at a couple of figures here, this figure indicates that we have different means. So here's mean 1 and mean 2, but we have the same standard deviation. So the figures here, the probability density functions, look pretty much the same, except for they're shifting either to the right or the left, depending on your perspective. In this case, we have two normal distributions, right? But they have different standard deviations. So the spread is different. Now, mind you that like any probability density function, they always have to account for 100% of all values. So in other words, they have to integrate. Again, we're dealing with a continuous distribution here. They have to integrate to 1. So regardless of the shape, they still account for 100% of the entire distribution. When I say 100%, and 1, because 1 times 100 is 100, right? So multiplying any value by 100, so like for instance 0.9 times 100 is 100%, right? So you're multiplying a proportion by 100, you get to 100%. So if we multiply 1 by 100, we get to 100%. Sorry for that basic stuff there, but I want to make sure it's clear. So the total area under the curve, that's how we actually calculate the proportion, is by calculating the area, the actual area under the curve. If you go back to this initial figure, if you look at these little rectangles here, the smaller they get, the more close they get to this line. See right here, we have part of this rectangle is above the line, and we need to shrink these so much so that they pretty much are completely below the line. But the area of each of these rectangles is its width times its height. So that's when we talk about the area under curve. That's how we actually identify proportions. If you recall, the area of one of those rectangles is a probability, right? Because the height of this curve is essentially it's the frequency of values at that point, right? And with a continuous variable, we don't deal with points, we deal with areas, because again, the probability of any one point on a continuum is actually 0, because it can be divided so many ways, right? We know a lot about this distribution. First of all, it's symmetrical, so 50% of the distribution is below the mean and 50% is above the mean. Now this picture, I don't have a line here, but here I have a line cutting the distribution in half. You look at this, for instance, this one on the right with the mean mu2, the line divides it perfectly, or as Captain Picard would say, the line stops here. I like his accent, Jean-Luc Picard. So 50% of the distribution is above the mean and 50% is below the mean. Because of that, we know that, well, the proportion is equal to a probability. So let's say we have a person who scores at the mean value for whatever we're dealing with. That person will score above 50% of everybody else and below 50% of everybody else. So you got to remember these things. We also have this really neat rule when we're dealing with the standard normal distribution. A standard normal distribution has a mean of 0 and a standard deviation of 1. So we're going to be dealing with this distribution a lot now. We know that with this distribution, we know that 68% of all values are between plus or minus 1 standard deviation of the mean. 95% of all values are between plus or minus 2 standard deviations of the mean. And 99.7% of all values are between plus or minus 3 standard deviations of the mean. This is really, really important for you to know this. And you need to mentally play around with this a bit. In this figure where we have 2 standard deviations above or below the mean, plus or minus 2 standard deviations of the mean, we account for 95% of all values. So if I was to ask you what proportion of the values are beyond plus or minus 2 standard deviations of the mean, that means outside. They could be either above 2 standard deviations of the mean, or they can be below. That's why I said either or. And you should recall from some of our properties of probabilities that these are mutually exclusive events. You can't be both above and below plus or minus 2 standard deviations of the mean. So you can add these together. Well, we have 2.5% here and 2.5% here. Why? Okay, well, let me explain why. If 95% of all values are between plus or minus 2 standard deviations of the mean, within plus or minus 2 standard deviations of the mean, the complement of that situation, the opposite, right? The complement, complements cannot occur together, is being outside plus or minus 2 standard deviations of the mean. So if 95% are within plus or minus 2 standard deviations of the mean, 1 minus 95 is 5, so 5% is outside, right? This is an either-or situation because we're above or below, plus or minus 2 standard deviations above or below the mean. So I have to take that 5% and cut it in half. Again, this is a symmetrical distribution. So what that leaves us with 2.5% here and 2.5% here. This will be extremely important when we start doing statistical testing. One point about this is that the height of a distribution indicates its prevalence, for lack of better words, or frequency, how many individuals score in that range. So clearly in this distribution, this is actually a distribution of, this is a distribution of the IQ test, because the IQ test has a mean of 100 and a standard deviation of 15, right? So if somebody scores exactly at the mean, that's 100%. Their score is 100, right? That's right in the middle. That's about 50% of the distribution and below 50% of the distribution. Notice as you go further away from the mean, like to 115, the graph or the chart or the lines here are lower, right? So this means a smaller proportion of the population are scoring around 115, just like a smaller proportion of the population scoring around 85. As we get further and further out, like say 2 standard deviations from the mean, so the mean is 100, standard deviation is 15, 15 times 2 is 30, 100 plus 30 is 130. So a person scoring at or above 130 is very rare. You can see the height of this figure is very, very low. Or this function, I should just call it function. The height of this function is very, very low. It's very close to the x-axis. The same with somebody who scores 2 standard deviations below the mean, 70 and beyond, in the negative direction. The height of the function is very low here. So you need to know this, that the further away you get from the mean, the lower the probability of that event. As a matter of fact, once you get out this far, like either 2.5% above or 2.5% below the mean, an individual has only, like an individual between 130 and infinity, this goes on to positive infinity, this side goes on to negative infinity. These individuals scoring in here are less likely to belong to this population. In fact, they only have a 2.5% chance of belonging to the general population. So that means they may belong to some other population. The same with individuals down here. They only have a 2.5% chance of belonging to the population with a mean of 100 and standard deviation of 15. It means they probably belong to some other population. Please digest that, keep that in mind, play around with it. Hey, let's go to a separate topic now. So we talked a little bit about the normal distribution, and our goal is to have, we'd love to have a normal distribution. In fact, we can convert any distribution if the sample size is large enough, and we'll get to this later. If the sample size is large enough, we can convert any distribution into a normal distribution. And what's large enough? It's usually around 30, something like that. But there are times when we are working with distributions and we're in our data analyses when we want to make something look more normal than it is, because that'll help us in our analyses. Like say if we're doing a regression analysis, multiple regression analysis, and our outcome variable is continuous but it doesn't follow a normal distribution. So we can actually normalize it to a certain degree by doing a transformation. And there are a variety of transformations that we can use. Probably the most common transformation you'll see when someone is trying to normalize a variable. Again, the variable, if we look at its distribution, like when we did our frequency, our histograms for your first assignment, you saw that they didn't all look like a bell curve. Some of them looked a little different. Some were skewed in one direction, so they had a tail longer on one side than the other. So we can deal with that, these anomalous distributions, by transforming them and making them normal. So one of the most common ways to normalize a transformation is to take the natural log of the value. So a natural, and we did this in EPI where we were doing some of our calculations. We did already learned about log transformations, natural log transformations. Well, you can do a transformation with any kind of base, and when the base is E or Euler's number, it's called a natural log transformation. The natural log transformation kind of flattens things a bit, flattens the curve a bit, like Dr. Fauci said, flattening the curve. So that's one thing that we do often, and we may do that later on when we're conducting regression analysis. We may just do that for the sake of learning to see what happens. Now, I already talked a little bit about the standard normal distribution. We did the 68, 95, 99.7 rule. So, and I mentioned how we can really turn distributions into a normal distribution. One way we do that is by standardizing the values. We standardize values for the standard normal distribution by converting them into what we call z-scores. Z is, it doesn't matter what you call it, but we tend to call it z-score. We calculate these z-scores. The way we do it is well, this is actually very interesting. This equation is very, very self-explanatory. We convert a value into a z-score by subtracting the population mean from the value and then dividing by the standard deviation. This puts it in terms of standard deviations, in standard deviation terms. So basically, a z-score is a certain number of standard deviations from the mean. So if our mean is 100, like we had for the IQ, you probably had mean of 100, standard deviation of 15. If I start at the mean value and let x equals 100, so somebody scores 100, and the mean is 100. 100 minus 100 is 0, so that sets the mean at 0. If we know our standard deviation is 15, right, so the denominator here is 15, and we take an individual who has a score of 115, subtract the mean from it, we get 15. 115 minus 100 is 15. 15 divided by 15 is 1, so we're one standard deviation above the mean. If I take a person who scores 85, 85 minus 100 is minus 15. Minus 15 divided by 15 is minus 1, so that individual is one standard deviation below the mean. So in a sense, we're putting everybody's score into standard deviation units. This standard normal distribution is normal, and the way we indicate the distribution of a variable is by this approximation sign, a tilde, I think that's called. So z is approximately normal with a mean of 0 and a standard deviation of 1. So you should have seen this before when we did the binomial and the Bernoulli. We had this notation here. So you could read this as z is a continuous random variable distributed as normal with a mean of 0 and a standard deviation of 1. Then we can go into our textbook, and in the back of your textbook you have this conversion table that allows you to convert any z value into a proportion. Now this is a nice table. This is a really, really nice table because this one starts at negative infinity and goes up to the z value. Not all tables are like this. Some tables give you only half of the distribution. Like in my undergrad class, I teach with the half of the distribution. It actually is more instructive. It's like when I teach skiing and I tell skiers, you don't need your poles, throw away your poles and let's work on skiing without the pole. It actually turns you into a better skier. Same here, but you're lucky your textbook gives you this, and I'm not going to go against what your textbook gives you. However, hopefully you'll be able to figure this out after we deal with all these different anomalies that we come up with. So for instance, a person, let's see, if somebody has a z-score, so this is how you read it. You start here, you get the tenths value, so you get, for instance, 1.1, and then you add the hundredths value. So the probability of a value of 1.10 or lower is 0.8643. So I go 1.10. This would be 1.11. This would be 1.12. So you read across. Here we have 1.96. Now we picked this one specifically because 1.96, the probability of value 1.96 or lower is 97.5. So that means there's 2.5% of the distribution above that, because 1 minus 97.5 is 2.5. And as you'll recall, we talked about that already, right? We talked about being 2 standard deviations from the mean. 1.96 is basically 2, right? And I mentioned how that value is going to be important to you later on, right? So you'll notice that these z-values allow you to place an individual in relation to the population. Like if you have a z-score of 1.96, we converted the person's raw score to the z-score, and your z-score is 1.96, you have scored at or above, and I say at or above, okay, again, because this value has a very, very small probability itself, right? Probability of 0. You've scored at or above 97.5% of the entire population. That's what we call a percentile. Okay, percentile. So you've probably heard of percentiles somewhere down the line. We use them in public health all the time. We use them in medicine all the time. Like if you have a baby, you take your baby to the healthcare provider, your infant to the healthcare provider, you'll get a head circumference, you'll get weight and height, and you'll get the relation to the population as a whole. You'll get a percentile. And you want your infant to score within the normal range. You don't want them to be above or below to some extreme level, like what we're doing with these tables here. That they'll say that they're exceptional in some way. Could be exceptional in a good way, could be exceptional in a bad way. And that's how we find medical problems, by compare. And the same thing with body mass index for your age. You look at your BMI and see how you compare to the population. That's how you find out if you're exceptional in a bad way or in a good way, right? So let's see, here's an example. If we have an individual who scores whatever this is, scores 40, and the population has a mean of 39 and a standard deviation of 2, to calculate that individual's z-score, we go 40 minus 39 divided by 2. The 2 is the standard deviation. We get 0.5. And let's see if I can look it up. 0.5 is in this, it's 0.5, just 0.5, so it's 0.50, right? A person with a z-score of 0.50 is at or above 69.15% of the population. 69.15% of the population. So I ask you, what proportion of the population scored above an individual with a z-score of 0.5? So you should appeal to these properties of probabilities. We know that that the area under the curve is 1. So if we integrate across all possible values from negative infinity to infinity, we have to come up with 1, right? And what we know about complementary events, either you can be at or above 0.5, at or below 0.5 or above 0.5. You can't be both. So we know we can sum those up and they must equal 1. So to find the area above, at or above, again, I can say at or above for both cases because this point is probability of 0. The point, you can either say point above or at or above 0.5 is going to be 1 minus 0.6915. So there's a 31, so I rounded up to 31, there's a 31% chance of scoring above, at or above 0.5. Or we can translate that to at or above 40, right? Because we just standardized it in order to do that calculation, but we have to bring it back into our original scale, whatever it is, right? Okay, let's see. So that's what I talk about here. Ooh, this is fun. Often we want to know what's the probability of somebody scoring between 2 points, right? So we're not always interested just in percentiles. So for instance, here, this value B gives me the probability that somebody scores below B. This value A gives me the probability that somebody scores below A, that area. See that area in blue, right? But if I'm interested, what's the probability that somebody scored between A and B? Well, what I would do is take the probability that Z is less than or equal to B and subtract from it the probability that Z is less than or equal to A. So then I would get this probability here. Do I have an example? Probably. So, but make sure you understand that. So it's just a matter of subtracting out the little area here because you're only interested in the probability between A and B. I have a few examples coming up. So get to know, understand how we do this, okay? But let's go to some examples, exercises. So let's go to exercise 7.12. This is from your textbook. Let me grab my textbook. Hello, textbook. Hello, textbook. This is on page 172. Page 172. Alrighty. All right. Exercise, it says 7.12. All right. Standard normal proportions. Use table. Oh, I do have one. Okay. Use table B to find the proportion of a standard normal distribution that is below minus 1.42. So let's get that. Page 1. Below minus 1.42. Let's see. Oh. All right, so I can just show you how to do that because apparently I started at 7.13, but I asked you for, what did I ask you? I asked you for 7.12. All right, so let's go to your textbook. So now I'm in my textbook and I need to go to the table. It says a table B. All right, I'm going to go to table B. Hey, where's table B? ¿Dónde está table B? Sorry for the delay here. I gotta find. Okay, here it is. Table. What's this? Actually says appendix B. All right. So it asked me what's the proportion of a standard normal distribution that is below minus 1.42. Wow, table B is so awesome. It gives you the negative values. So you look for the negative 1.4. It says 1.4. So you look for a negative 1.4 in the tenths column. So I'm now on page 542 of the textbook. I find I see negative 1.4, and then it says negative 1.42. So under the hundredths column, so the first, second, third, fourth column, the first column says Z tenths, the second column is labeled 0, 0. The third is 0.01, the fourth is 0.02. So I find the fourth column, and where the two intersect, where negative 1, the row that is labeled negative 1.4 and the column that's labeled 0.02 intersect, they intersect at 0.0778. So that would tell me that 8% of the population values are at or below minus 1.42. Now note in exercise 7.12 it says below 1.42, but I say at or below. Again, it does not make a difference. Again, the probability of any one value is 0 on a continuum. So what's the proportion above 1.42? So now we look for, you should be able to solve this in your head because this is actually not that hard to do. Because if you remember, this distribution is symmetrical. So, but I'm not going to say anything more than that, and you'll see in a second. So I go to page 543, and I look for 1.42, and you should get 0.9222. 0.9222. So that's the proportion that is at or below 1.42, right? Well, they say they want to know what proportion is above it. So I bet you can't guess what it is. So let's see. It's 1 minus, I said 0.9222. Hold on, let me clear. 1 minus 0.9222, and we get, oh look, it's the same value that we got before. That's because it's symmetrical. So use your knowledge of this figure. You don't even need to do these calculations. You can just know it's symmetrical. All right, let's go to below 1.25. What proportion of the population is below 1.25? So we're still going to be on page 543. You look for the column that's labeled 1.2. I found it. The row, excuse me. Look for the row that's labeled 1.2 and go across it to find the hundredths value, 0.5. Okay, I found it. And look for where they intersect, and I get 0.8944. All right, so we know that 89% of the values are below 1.25. Last but not least, what proportion of the values are between 1.42 and 1.25? All right, 1.42, we knew. Okay, this is going to be a little more complicated, so just watch what I do. 1.42 is greater than 1.25. So 1.42 is further to the right of the mean than is 1.25, correct? And if you recall, what we get in the table is everything to the left that's accumulated from lowest to highest up to 1.42 or up to 1.25. So let's see. So let's start with the higher value. The higher value is 1.42, and we just calculated that a little while ago. We found that the probability of a value being at or below 1.42 is 0.9222. So let's start with that, 0.9222. Now we're going to subtract. We saw the equation in the text in my lecture notes a couple of moments ago. We're going to subtract from that the proportion that is below 1.25. So we just calculated the probability of being at or below 1.25, and it was 0.8944. So we subtract 0.8944, and we get 0.0278, or basically 3% of the population has a z-value between 1.42 and 1.25. Get it? Alrighty. Alright, that's easy peasy lemon squeezy, as they say. Alright, let's go on. Next item is 7.13. 7.13. Let's go 7.13. Alzheimer's brains. The weight of brains from Alzheimer's cadavers varies according to a normal distribution with a mean of 1077 grams and a standard deviation of 106 grams, and they give you the reference there. So this is the population value, right? So the population mean is 1077, the standard deviation is 106. The weight of an Alzheimer's free brain averages at 1250 grams. What proportion of the brains with Alzheimer's disease will weigh more than 1250 grams? That's a good one. Oh, I love these problems. I love them. I hope you love them too. All right. So this is our mean, population mean, so it has a mu and a sigma for a standard deviation, right? This is our x value. This is our variable. Let x equal the brain weight, right? Is normal, brain weight in grams. So we're trying to find what's the probability that x is greater than 1250 grams. Okay? So we take our x, we're going to convert this into a z-score so we can use this z table. Now, why we have a table? Because there's some people have gone through great lengths to calculate these values for you so that it makes your life easier. In the real world, we don't always have all the values, and we have to use calculus to calculate these values when our distribution is not specifically normal or it varies in some way. So just understand that some people have done this great service for you and did all these calculations for you. That's why we like to use the normal distribution, because we know everything about it. So our x value is 1250. So we're going to turn it into a z value, so subtract the mean and divide by the standard deviation, and we get a value of 1.63. So this is our z-score. So this, just to make this clear, a value of 1250 is 1.63 standard deviations above the mean. So it's getting closer to 2 standard deviations above the mean. So we go back to table B. So we need the table B will give us the probability of a value at or below 1250 grams. So I go to table B. Should have left that open. I should have left it open. I should have. I could have and I should have. Okay, it's on page 543, and I look for 1.63. I go down to the row that says 1.6, and I go across to the column that has the hundredths value 0.03, and I get 9.9484, which I write down here. But the question asks the probability of somebody having a brain larger than 1250 grams, right? Well, given that we know that either you can have a brain that's below 150 grams or above below 1250 grams or above 1250 grams, these are complementary events, and we know that this standard normal distribution, the area under the curve is 1, so it must integrate to 1 to calculate the probability of a brain having a weight above 1250 grams is 1 minus the probability that it has a weight at or below 1250 grams. So it's 1 minus 0.9484, and it looks like that's a 0.0516, or there's a 5% chance. Knowing these little properties is going to make a big difference. Alrighty. Let's go to the next item. The next item is 7.15. 7.15. Page 172. Oh, this is fun for me. I hope it's fun for you too. All right, 1.5. Why did I pick 7.15? All right, probably for this reason. Find the following percentiles. Oh, this is fun. This is the opposite. So this means finding a z value that is at or above 10%. When you see these are the percentages here, right? Or percentiles. So now we have to convert these to z-scores. So this is kind of like working backwards. So what's the z value that is associated with the 0.10? 0.10. So we're going into the table, right? So this is the 10th percentile, right? Because this, you multiply by 100, it's 10%. We're going to go into the table, into the body of the table, because the values in the body of the table are the percentiles. So we need to look for a value of 0.10. So now we're not looking at the first row yet, and we're not looking at the first column yet. We're looking within the table and trying to find a value that's 0.10, or at least very, very close to 0.10. Wow. Okay. I'm going down the first row to find a value that's close to 0.10. Let's see, 0.10. Ooh, this is tough. Okay, if I go down to the row that's labeled minus 1.2 and go across that row, I'm getting closer and closer to 0.10. Say like at minus 1.27, I'm at 0.1020, and move to the right to minus 1.28, I am really close. Minus 1.29, I get a little further away. So it's probably 1.28, and yes, indeed, it's minus 1.28. So that's a z-score associated with it being at the 10th percentile. Let's do some more of these. We'll keep on doing them until you dial them down completely. Excuse me. All right, the next one is the z-score associated with a percentile or being at the 35th percentile. So it says z 0.35. All right, well, by the way, as long as it's below 0.5, you know it's going to be negative because half of the distribution is below the mean and half is above the mean. All right, 0.035. So again, I'm looking in the meat of the, I could call it the meat of the table. It's like you're digging into the meat of the table. I'm looking for 0.385 and I'm seeing threes. Okay, if I go down to the row that is minus 0.3, I got minus 0.3, so I'm looking for 3.5. How about that? Yes, 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 yes. Okay. If I go across the row that's labeled minus 0.3 and I get to somewhere between 0.08 and 0.09, so I need 0.35. Which one is closer? I would say 9 is closer, so this value should be something like minus 0.39. Well, actually, I did it between. I went minus 0.385. I did it between the hundredths value of 0.08 and the hundredths value of 0.09. So I went to minus 0.385, minus 0.385. There you go. Okay, so you find the percentage within, or the percentile within the table, and then trace out to the rows in the column to find the z-value. Let's go to z of 0.74. So now this is a 0.74 is above 0.5, so you know it's going to be a positive value. 0.74, so let's see. So I'm on page 543, and I need 0.74. Okay, I'm on the row that says 0.6. 0.74 is between, it's somewhere between 0.64 and 0.65. In this case, I chose 0.64. Okay, because the probability of being at or below 0.64 is 0.7389. The probability of being at or below 0.65 is 0.7422. So it's a little bit closer to 0.64. So here, this one I went in between, this one I went at. You know, as long as you make a good argument for it, it doesn't matter really which one you choose, because I mean that's where it is pretty much. Z of 0.85, well we know that it's going to be again positive because 0.8 is way above 0.5. So we look for a value of 0.85. I'm looking at the table at 1.0, and I go across 1.04 looks like the best one to me because that has a probability of 85%. So the value that at the intersection of 1.0 and then the hundredths 0.04 is 0.8508. And finally, last but not least, a z-value associated with 0.999. Yikes. 0.999. So it's going to be way down. That's going to be very, very far above the mean, right? So the mean is at the 50th percentile. This is almost basically it's at the 100th percentile, right? So 0.999, we go across, and I actually can find the value. It's on page 543. It's 3. Well, there's a couple that say 0.999. Some are like 3.85 or something like that, or 3.09, 3.08 or 3.09. Yeah, so I chose 3.09. Fun exercise, right? Make sure you understand that. Oh, I actually did 7.12, but I did it backwards for some reason. Yeah, that's silly, man. What the heck's he doing? So you have the values there. So this is what we did earlier. So good. I'm glad I did a All right, let's go to 7.19. 7.919. A 6'7" tall man. Whoa, 6'7" tall man. Have you ever wondered why a man who is 6'7" tall seems so much taller than a man who's 5'10", even though he's only 13% taller in relative terms? Okay. Let us assume that male height is normally distributed with a mean of 70 inches and a standard deviation of 3 inches. What proportion of men are 5'10" or taller? What proportion of men are 6'7" or taller? I like this one because I'm 6 feet tall, so I like knowing that the mean would be lower than my height. So I'm tall then, right? All right, so we have the population of mean of 70 and a standard deviation of 3 inches. We want to know what's the probability of a value that's greater than or equal to, this at 5'10", right? 70 inches. So, well, that's pretty easy. It's 50%, right? Because our mean is 70, so using our z formula or z equation, take x minus the mean divided by the standard deviation. 70 minus 70 divided by 3 is 0. So anything divided into 0 is 0. And with a standard normal distribution, 50% of the population is at or below 0. So if you're 6'10", you're smack in the middle. You're just above 50% of the population. If, on the other hand, you are, 79 inches? Is that what he said? Yeah, 79 inches, or 6'7". Well, it's 79 minus 70 divided by 3, which is 9 divided by 3. You're 3 standard deviations above the mean. Well, if you recall if you call this beautiful rule, this 99.7% rule, this is an interesting one. Okay, this is actually an interesting one, because the 99.7% rule is the proportion of the population that's excuse me, between plus or minus 3 standard deviations of the mean. So I like the way I solved this here. So I divided this by 2 to find out what proportion of the population is between 0 and 99.7%. So that half of, right, 0 and whatever half of 99.7 is. So let's see, what's half of 99.7? So that means between 0 and 0.997 divided by 2, right? We get 0.4985. But that's between 0 and 3 standard deviations above the mean. To know what the actual percentile is, and this is where you really need to understand this distribution. So this is just between 0 and 3 standard deviations above the mean. If we want to know what the percentile is, what proportion is accumulated from negative infinity all the way to 3 standard deviations above the mean, I have to add 50 to this. So I add 50 plus 0.5. Right? It's 99.9985. Now, last thing I want to know is what proportion of the population is at or above 3 standard deviations of the mean. Well, either you can be what is it, 6'7", or above or below 6'7", right? So they're complementary. So to find out the proportion that's above this, I have to subtract it from 1. So let's get 1 minus 0.9985 equals 0.0015, right? And that's what I get here, 0.0015, and you multiply that by 100, you move the decimal place 2 decimal point 2 spaces to the right, we get 0.15 or 15%. 0.15%. So it's a very, very small percentage of the population. And here I just looked at the, I guess I looked at the table here. and I came up with 0.13%. So this is a good one to practice on. Make sure you understand how we derive these values logically. So I didn't even really need to go to the table, right? I didn't need to go to the table at all. So I use this 68, 95, 99.7 rule. Or you can go to the table and do it. So if I went to the table, so this is, I did this a long time ago, so I'm assuming I got this from the table. Go to 0, I'm looking for, yeah, that's exactly what I did. So if we go to page 543 and you look at a z-score of 3.00, it's 0.9987, so that's the proportion that's at or below 0.9987, so it's 1 minus that would be at or above that level is 0.0013. So look, I'm not off by that much. Like if you did this, of course I'd make it correct. Okay? I love this kind of stuff. This is where you play around with things and you see where there are minor differences when you make calculations. It's just a lot of fun. All right, let's go to the next one. All right, we did that. 7.2, the tall person, and 7.23. Last one, 7.23. Suppose that scores on the biological sciences section of the medical college admissions test, MCAT, are normally distributed with a mean of 9.2 and a standard deviation of 2.2. Successful applicants to become medical students had a mean of 10.8 on this portion of the test. What percentage of applicants score at 10.8 or greater? I guess it's not that hard. That's kind of like what we've been doing. Let's go to the next figure. Where's the next one? Let me go to the next one. I have you here somewhere. Nope, it doesn't show. All right, let's see. Where are you? Where are you? Let's close this one. I have this. I do have. Here it is. All right. Mean is 9.2. The standard deviation is 2.2. Here we're actually dealing with a mean, so that's why it's not an individual value, but it kind of is an individual value. So 10.8, the probability of x being above 10.8, so it's 10.8 minus 9.2 divided by the standard deviation. We get 1.6 divided by 2.2, so we get a z-score of 0.73. Again, it's above 0.5, so it's going to be positive. So let's look at back in the table again. We're going back to table B, appendix B. Back to appendix B, and we're looking for a z value of 0.73. And I get 0.7673, right? 0.7673. So that's the percentile, right? So this is the proportion of individuals at or below a z value of 0.73. So to find out the proportion that's above that, and again, they're mutually exclusive, either you can be below or above, we subtract that from 1. So it's 1 minus 0.763, you get 0.2327 or 23%. Okay, that, my friends, is it. And we can review as much as you want with this and do more practice problems. There's plenty in your book. Have a good day. Bye.